So hello everyone. Today we are going to start from where we have left in the last class. So in the last class we have seen about the Cmos VTC, how to obtain the Cmos VTC from the intersection of NMOS and PMOS characteristics. And thereafter we have seen in detail that what are the various regions on this Cmos VTC and what is the importance of these regions. As we can see here in this graph, just for the revision, that there are 5 regions, and these 5 regions are basically, you can see in the diagram, and the regions in which this NMOS and PMOS operates in these 5 regions. So you can see that they operate in different regions. Okay, so as you can see that in region A, our NMOS works as in cutoff, whereas our PMOS works in the linear region. Then in the region B, okay, starting from the VTN to the point till your V out is greater than Vin minus VTN. So up till that region, your NMOS is in saturation. So basically your NMOS is in saturation in region B and region C, whereas PMOS is in linear region in region B, and whereas it operates in saturation in region C. So you can see that in region C, both NMOS as well as PMOS operates in saturation region. Then comes the region D, and in the region D, things are exactly opposite. So NMOS operates in linear region, whereas the PMOS operates in saturation region. And in region E, your NMOS is in linear region, whereas your PMOS is in cutoff region. And that is why the output voltage is 0. Okay. And these regions are important because we have like various important voltages like VIL, VIH and VTH, along with VOH and VOL. So this VIL, VIH and VTH lies in these different regions. Okay, so this is what we have discussed in our last class, that our region, in region B, our VIL lies. Okay, so VIL basically is in region B, and then your VIH is in region D, whereas our VTH is in region C. So keeping this into mind, let us move on to the derivations of this important voltages which are important for any inverter. So whenever we have to determine the performance of an inverter, we have to determine this voltages VIL, VIH, VOL, VOH as well as VTH, and this voltages will help you to determine the noise margin of your inverter. So let's move on and try to understand that how to find our VIL. So as we have seen in our last slide, that our VIL falls in the region, basically as you can see, it falls in the region B. So in region B, if you will see, so your NMOS operates in saturation region, and your PMOS, from this table you can see that in region B your NMOS is in saturation region, whereas your PMOS is in linear region. So we have to use the drain current equation of saturation for a PMOS and the saturation current equation, the linear current equation for PMOS, whereas the saturation current equation for NMOS. And you see, in the last, during the discussion of your Cmos inverter, as you can see from your this particular thing, that during the DC behavior, as we are trying to analyze the DC characteristics. So if we try to analyze the DC characteristics, so then your CL, the load capacitance, we treat it as an open circuit, and so your drain current which is flowing through your driver is equal to the drain current which is flowing through the load. So load here is, let's say, PMOS, whereas the driver is NMOS in one case and the opposite in the other case. So point is, like, whatever is your IDN, the current flowing through your NMOS will be equal to the current flowing through the PMOS. So let's say or denote that by IDP. So basically your IDP will be equal to IDN. So in this diagrams, if you write, so you can see that IDP will be always equal to IDN. Okay, so that's what is important. So if you'll see this, if you'll keep this into mind, particular thing, then we can see that IDP is equal to, if your IDP is equal to IDN, then and this happens, this is always true. So then if we equate these two currents, then substituting the saturation current equation for NMOS, whereas the linear current equation for your PMOS, and substituting, you see, when this is the equation, if you'll see this in terms of GS and DS. So if I write the equation for NMOS in terms of gate to source voltage which is applied to the NMOS, its threshold voltage, and then the gate to source voltage of PMOS and the threshold voltage of PMOS and the drain to source voltage of PMOS. So if I write the equations, then it will become something like this, which you can see here. So the equation will become Kn by 2, where Kn is your process transconductance parameter. Okay, so we have already defined that what your Kn is nothing but mu n Cox W by L. Okay, so you see the saturation current equation you can see here, and we have equated the saturation current equation of NMOS to the linear current equation of our PMOS. Then, as we have seen in the last class, that how to denote VGSN in terms of Vin and Vout. So to denote this various voltages like VGSN, VGSP and VDSP in terms of Vin and Vout, we can write the above equation in a different way in terms of Vin and Vout. So you see the equation will become as VGSN is equal to Vin and your VGSP is equal to Vin minus VDD. Okay, so see that, and Vout is equal, VDSP is equal to Vout minus VDD. Okay, because it is drain to source, and drain is at Vout potential and source is at VDD potential. Okay, so substituting all these things, if we rewrite the equation, then it will become the equation as seen in the equation number 2. Okay, then later on, if you further solve it, and you see, as we want to determine what VIL. So if you want to determine VIL, then what we have to do is at VIL, I mean, how you define, basically the definition of VIL is the point where your dV out upon dV in, okay, this is equal to -1. So to find VIL, first of all, we have to get the equation in terms of dV out and dV in. Okay, so dV out upon dV in, somehow we have to get this into the equation. Once we are able to get this dV out upon dV in into the equation, then we can substitute -1 for dV out upon dV in, because we want to find VIL, and with VIL, this is what the situation is, this is what the condition is. So at VIL, the dV out upon dV in have to satisfy the equation as have to satisfy the condition as -1. Okay, so then you see at VIL, at when your input is equal to, as we are changing input continuously, so at when your input is equal to VIL, at that particular instant your dV out upon dV in will be equal to -1. So if we substitute all these things, like V in, instead of V in the previous equation, you substitute everywhere VIL. Okay, and then in the previous equation, if we derive it with respect to V in, then we can write the equation as you can see in the equation number 3 this, okay. Then this equation, in this equation, if you substitute dV out upon dV in is equal to -1 and rewrite it in terms of VIL and the other parameters. In the previous equation you cannot see VIL anywhere, but this VIL you get if you substitute V in is equal to VIL, okay, because V in is changing, and to derive either any of this VIL or VIH we have to, or VTH, we have to use that particular parameter instead of Vn, because Vn is changing, and for a particular situation, for a particular condition, that voltage, that input voltage will be called either VIL or VOL or VTH. So whatever is the situation, whatever condition it satisfied, accordingly it will be given a certain name. So as it is satisfying the condition of dV out upon dV in is equal to -1 on the lower side, okay, so then we call it VIL. So then your VIL, if you write the equation, then it will become twice of V out plus VTP minus VDD plus KR. KR is nothing but it is the ratio of process transconductance parameter for NMOS and the PMOS, okay. So you see it is KR is equal to Kn upon Kp as defined in the lower equation. So this equation will become something like this. So this is the equation for VIL, okay. So this equation, and in this equation if you will see that VTP is negative. So while substituting the values in a problem, if you want to solve a problem and want to determine the VIL there in a design, for a design case, then obviously we have to use the values given in the problem or according to our design scenario. So our VIL formula in general will look like this. Now suppose we want to determine, now this is what the derivation for VIL is. Now suppose if you want to determine VIH, okay, it is the same thing, dV out upon dV in is equal to -1, but for a higher value of V in, okay, for a higher value of the input voltage. So if you do this and try to find it out on the same lines, same we have to do, but rather the other thing is in the same equation, I mean the same, all the steps will be same, but rather than using the saturation current equation for NMOS and the linear region equation for PMOS, we have to use the linear region equation for NMOS and the saturation region equation for our PMOS. Why it is so? Because VIH will fall over, if you see this particular diagram of VTC, you can see that VIH will fall in the region D, okay, and in the region D from the table if you will find, then you can see that your NMOS operates in the linear region whereas your PMOS operates in the saturation region. So if you substitute these things, same thing, okay, but now if you have to write the equation, then you will write the equation as Kn upon 2, then okay, this will be, I mean your NMOS is in the linear region, so the equation will become Kn upon 2 twice of VGSN minus VTN into VDSN minus VDSN whole square, right? And that will be equated to your, why it will be equated, because in the earlier discussion we have seen that your NMOS current, whatever drain current is flowing through the NMOS is equal to the drain current flowing from the PMOS, okay. So you see that is what the thing is. So you have to substitute this here. Then simultaneously you can write the equation, and this is the magnitude of the currents, okay. So I am talking about the magnitude of the current rather. So you see then this particular thing you can solve it, okay, and after solving you will get the equation in terms of VIH and the other parameters. You can try this equation by your own, and if you have any doubt you can either ask me or you can refer the book as well, okay. So this is very simple equation, but I have just told you the method, and then you can try it by yourself, that how to do it, okay. Then moving on to, so this is how you have to find the VIL and VIH in general for your any CMOS inverter. Now later on we will see that these equations will be useful to determine the VIL, VIH for any of the like complicated gates as well. for the complicated circuits as well. So these are the basic equations which will help you to understand the analysis of the DC analysis of the further circuits, for the further complex circuits. Okay. So this was a short discussion about VIL and VIH. Now moving on to the other important parameter, which we call as the threshold voltage of the inverter itself. Okay. So it is the transition voltage from the lower side to the higher side, or from the higher side to the lower side of the inverter itself, not the threshold voltage of NMOS or the PMOS, but it is the threshold voltage of the inverter. So to determine the threshold voltage of the inverter, what we have to do is again the same reasoning what we have done to determine this VIL and VIH. The same logic we have to use to determine VTH as well. But now the situation is that the two devices will operate in the region C rather than region B or D. They will operate now in the region C because VTH falls in the region C. So if your VTH is falling in this region, then obviously both of your devices are operating in the saturation region, and therefore you will use the saturation current equation for both the NMOS as well as the PMOS. So writing the equation in terms of VGSN, the general form, then in terms of V in and VDS, V in and V out, okay, then you can substitute V in instead of V in, because V in itself is changing. So substituting V in is equal to VTH, okay, in the equation. Okay, then if you solve it further, then we will find that the equation for the threshold voltage of a CMOS inverter will become something like this. So the equation for the threshold voltage will be VTN plus under root of 1 by KR into VDD plus VTP divided by 1 plus under root of 1 plus KR. So this is what the whole derivation is. Okay. Now for an ideal inverter, if you talk about, this is the general equation. So whatever we have seen so far is the general equation. But if we talk about an ideal inverter, so ideal inverter is, what is an ideal inverter? Ideal inverter is an inverter whose, if we talk about in the general sense, then its characteristics we have seen in the very first diagram of this particular unit. So for an ideal inverter, the transition takes place at a certain instant, okay, from the high to the low or from the low to the high. So for that particular inverter, if you see, your threshold voltage will be exactly equal to 0.5 VDD. Okay, so it is equal to half of VDD basically. So for an, if you will substitute this here in this equation, so if you will substitute that VTN is equal to VTP, and for an ideal inverter, if you substitute the other parameters, then you will find that your VDD is VTH threshold voltage will be equal to half of VDD. Okay, so this was discussion about this. Now let's move on and try to find the thing for our symmetrical inverter. So symmetrical inverter, okay, so this is what your ideal inverter is. So ideal inverter, if you talk about and you try to find the this ratio in this particular equation, of this threshold voltage, if you substitute your half of VDD instead of your this VTH, so because it is an ideal inverter, so you take this VTH ideal is equal to half of VDD, and this inverter we are calling it as a symmetrical inverter because the noise margins are symmetrical, the characteristics are symmetric across the center line. So that is why we are calling it the symmetrical inverter. So for the symmetrical inverter, if we see the things, then, and if you write the equation in terms of this Kn upon Kp for an ideal inverter and substitute the other values. So we are assuming that our VTN and VTP are equal, and let's say they are denoted by a certain voltage which is equal to VT0. So for a symmetric inverter, your Kn upon Kp will become equal to, let's say, 1. Okay, symmetric. So the ratio should be equal to 1. Now if you substitute this as 1, and if you solve this, if you substitute the value of the formula for Kn and Kp as well, so it will become Kn is equal to mu n Cox W by L and Kp is equal to mu p Cox W by L. And if we substitute them, this Kn upon Kp equal to 1, and solve the equation in terms of W by L of NMOS, to the WL by L of PMOS, then we can see that the W by L ratio is proportional to the mobility of the charge carriers. So W by L of NMOS is upon W by L of the PMOS is equal to mobility of the PMOS upon mobility of the NMOS. So mobility of a device is inversely proportional to the device dimensions, okay, W by L of the device. And if you substitute the typical values of mu p and mu n, so you see mobility of the electrons is like approximately twice to the mobility of the holes. So these are the typical values of mobilities. Okay, so if you substitute these typical values of mobilities, then we can see that the ratio will fall somewhere between, depends upon the geometry of the device. So if you keep on reducing the device length, then the mobility changes, okay, because of the velocity, saturation and the other things. So the mobility itself is affected. For the long channel devices, this mobility which we have written here is for the long channel device. So for the short channel device, it will be something different. So in general, this W by L upon W by L of PMOS will be equal to somewhere in the range of 2.5. So I have given you based on this ratio 230 upon 580, this ratio is coming 2.5, but it is not always equal to 2.5. okay, so this may vary somewhere. So the range is, let's say, 2 to 3. So if you what does it mean is, this 2.5 will not be exact value, but this 2.5 value can range from 2 to 3. So the point is, your width of your W by L of PMOS is twice or thrice, approximately twice or thrice to the W by L of the NMOS. If you want to make a symmetrical inverter, then the width to the ratios of the width W by L of PMOS and the W by L of NMOS should be kept in this range, 2 to 3. Then only we will be able to make the symmetrical inverter. Else, if we don't satisfy this condition, then our inverter will not be a symmetric inverter. Okay. So for symmetrical inverter, if we try to determine the VIL and VIH, then we have to just substitute the values in the previous equation which we have derived in this equation, VIL and VIH. So if you substitute Kr is equal to this 1, okay, because our Kr is equal to Kn upon Kp and we have like written it as 1, and we substitute these values in this equation and we write the equation in terms of the other parameters, then you will find that our VIL will be a simple this equation 1 by 8 of thrice VDD plus twice VTN, whereas our VIH will be equal to this. So there is another, to determine VIH, we can easily do that. This is VIH is equal to, or VIL, the basic equation is VIL plus VIH is equal to VDD. Okay, for a symmetrical inverter. So this is what happens. So for a symmetrical inverter, if you determine the formula for one of them, VIL or VIH, then you can subtract that from VDD, and whatever you will get will become the formula for the other parameter. Okay, so this is what is the importance of VIL and VIH, and how to determine this VIL and VIH for a symmetrical inverter. Now from these values, we can easily determine the noise margins. Okay, and you see, we have, there are 5 important voltages, but we have only derived 3 voltages. We have not derived anything for VOH and VOL. Why it is so? The reason is because it is a CMOS inverter, and in CMOS inverter we have full voltage swings. So when I say full voltage swing, so it means that our VOH reaches to VDD. Okay, so for a CMOS inverter, instead of VOH we will use VDD, and for a CMOS inverter, as we can see that our VOL reaches to 0. So we will use VOL is equal to 0 for a CMOS inverter. So if you substitute VOL is equal to 0 and VOH is equal to VDD, then we can easily find the noise margins for this device, for a symmetrical inverter, okay, or for any inverter. So we can find that NML is equal to VIL, whereas because VOL is equal to 0, So VIL minus 0 will be equal to VIL. And similarly, if you find NMH, then we can find that our NMH will be equal to VDD minus VIH, because VIH is equal to VDD. Okay, and for this symmetrical inverter, this noise margins will be equal. So the noise margin on the upper side will be equal to the noise margin on the lower side. So NML is equal to NMH, and each of them is equal to VIL. Okay, so you can substitute the values and can find them easily. Okay, now let's move on to the discussion of how this VTC changes with change of different parameters and on what factors this depends. Okay, so our VTC, basically this voltage transfer characteristics changes its, the shape remains same, but it shifts. Okay, so it shifts depending upon the value of Kr. So Kr is nothing but Kn upon Kp. So if our Kr upon this Kr, that is Kn upon Kp, is equal to 1, okay, this is the case of symmetrical inverter. So if we take a symmetrical inverter, and let's say for that symmetrical inverter or whatever inverter we are taking, the supply voltage is equal to 5 volt, the threshold voltage is equal to 1 volt. Okay, obviously I'm talking about the magnitude only. Okay, so if the threshold voltage is 1 volt, and if we see the characteristics, then we can see that the threshold voltage of the devices NMOS as well as the PMOS is equal to 1, but it doesn't mean that the threshold voltage of your inverter will be 1. It has to be determined by the previous equation which you have seen here in this slide. So to determine the threshold voltage of inverter, we have to use this equation. But let's say it is something. Okay, if you substitute the values there in the equation, then you can obviously find it. But the point which we want to discuss here is how this VDC shifts if we change Kr. So Kr is Kn upon Kp. So if we increase the W/L ratio of the NMOS, then our PMOS will become shorter than our NMOS. So if the width W/L ratio of NMOS is larger than the W/L ratio of our PMOS, then the characteristics which you will see will be the inner one. Let's say this is Kr is equal to 4. So when you talk about Kr is equal to 4, it is the W/L of NMOS is 4 times the W/L ratio of PMOS. In the previous case, both were same. So W/L of NMOS was equal to W/L of PMOS. Okay, symmetrical inverter. So the W/L of your NMOS is governed by this particular equation. Okay, so W/L of PMOS was equal to W/L of 2.5 times of W/L of NMOS for a symmetrical inverter. So for this, Kr is equal to 1, right? Okay, then if you increase this W/L, if you make it this equation, this previous equation, if that ratio is equal to 10, okay, rather than 2.5, W/L of PMOS to NMOS, okay, this you see W/L of PMOS to W/L of NMOS is equal to 2.5. So this case, if you make W/L 4 times, okay, so it will be W/L of PMOS will be your this, if Kr is equal to 4, then your VTC shifts towards the left side, whereas if your W/L of NMOS is smaller than the W/L of PMOS, then your Kr will be less. Let's say it is 0.25. So the characteristics will shift towards the other side. So this is what the difference between the two. Okay, so this is what you can see, that how your VTC shifts with change in Kr, right? Now in this particular characteristics, you can see that how our threshold voltage, okay, how our switching threshold voltage, that is VTH, changes with respect to VR. So in the previous slide, we have seen that how our VTC shifts. So from that particular slide itself, you can see that how our VTH is also changing. So you can see that as our Kr is increasing, okay, so switching threshold voltage is also decreasing. So Kr is Kn upon Kp. So if as you keep on increasing the W/L of NMOS, the threshold voltage keeps on decreasing. Whereas if you keep on increasing the width WL of PMOS, the switching threshold voltage increases. Okay, so this is what happens. So from this curve you can see that the variation is not in fact the linear one, okay, but it is a quadratic change you can see. So this is what is observable from this curve, that how our you can derive this thing by substituting different values in the previous equation of this threshold voltage. If you'll see this equation, VTH equation, and if you substitute different values of Kr for different values of Kr, you will find that, and if you try to plot the VTH for different values of Kr from this equation, then you will see that the plot will look something like this. So this is what we have plotted. So the variation, this variation is important, and this is how we can see it. Now we can see that how our drain current, and along with the drain current, the power dissipation, because you see power dissipation is basically DC power dissipation. I am talking about the DC power dissipation. So power dissipation is basically depends upon voltage into the current. So as you can see that the your voltage, the power dissipation, the current remains zero below the threshold voltage of the NMOS and above the certain voltage, which is VDD minus VTP. Okay, so the device will be off in this particular situation. Okay, so there will be no power dissipation in this region, or there will be no drain current from supply, okay, VDD. So you can see that your drain current starts increasing above your VTN, okay, because you see in the in this equation you can see that, in this diagram you can see that your VTN is equal to 1. So it is the drain current starts increasing above your threshold voltage, and then it reaches to the maximum value at the threshold point of the inverter. So your threshold voltage is somewhere between 2 and 3 of the inverter. So your drain current increases and reaches to the peak at this particular value, okay, where you're at VTH. Then from thereafter it keeps on decreasing, and at the voltage VDD minus VTP, which is here again becoming 4, because 5 minus 1, so 4. So you can see that the drain current is becoming 0 at this point. So this is how you can see that how your drain current varies. So if you'll get the chance to plot the curves, then from the in the lab, then you can see that this drain current will you can see that how it is you can plot it on the VTC. You can see that it becomes maximum at VTH. Okay, so this is what the significance of this particular curve. Now I can further see that if we keep we have seen that in the previous graphs we have seen that we kept VDD constant, but let's say if we change VDD itself, so up till certain value it will keep on working as an inverter, and that value will be the sum of your VTN and VTP. So up till and this VDD minus VTN and this VTN and VDD minus VTP, so up till that particular situation is satisfied, the circuit will keep on working as an inverter. Okay, so you see we are decreasing the voltages and still our inverter is working. Okay, and it is working as an inverter, although the shape is little bit, there is a change in the shape, but it is like still working as an inverter. But if we suppose keep on further decreasing it and go into a smaller range, okay, beyond let's say 0.5, which is the threshold voltage of an NMOS, then in that case it will behave in a different way. And basically if you'll talk about it, so it will have some hysteresis loop, but that we are not going to see it in detail here. So we just want to say that we just want to see here, as far as our introductory course is concerned, that if we keep on decreasing the VDD, then still our inverter works as an inverter. Okay, so with this particular thing we finish our today's this discussion, and this particular unit is over with this particular thing. This is the last topic which I wanted to discuss. But related to this, whatever we have discussed so far, I will like to discuss a numerical. I like to discuss a numerical with you. So that numerical is basically nothing but related to the determination of noise margin. So let's say we have to determine the noise margin for the circuit. For the given, the circuit have certain parameters. So this inverter is given, and the Cmos inverter have the following parameters. So VDD is given as something, let's say 3.3 volt. Threshold voltage of NMOS and PMOS is also given, and you can see that the threshold voltage of NMOS is not equal to the threshold voltage of PMOS. So obviously it is not a symmetrical inverter. Okay, because if it would have been a symmetrical inverter, then these two voltages, the magnitude of the two voltages should be equal. So as they are not equal, this is not a symmetrical inverter. Okay. Now you can further see that Kn and Kp is also given. So Kn and Kp is also given, and then the question says that calculate the noise margin of the circuit. So if you want to calculate the noise margin of the circuit, which is nothing but your NML and NMH. So if you want to determine NML, then NML is from your previous formula. We have seen in the previous slide that our NML becomes what? VIL minus VOL. Whereas NMH is equal to, from this slide you can see that NMH is equal to VOH minus VOH. So if you see this general thing, and if we, the point is we have to find this four voltages: VIL, VOL, VOH and VIH. Okay. So VOH, as it is in CMOS inverter. So as I have already told you that VOH and VOL will be something like we don't have to determine. So VOH will be equal to your VDD. Okay, because it is a CMOS inverter. So VOH will become 3.3 volts, whereas your VOL will be equal to 0. Okay, because it provides you, the CMOS inverter provides you the full voltage swing. So VOL will be equal to 0. Now we have to just find VIL and VIH. So how to find VIL and VIH? It is very simple. We have seen the equations in our discussion, and we saw that the VIL equation is something like this: twice of Vout plus VTP minus VDD plus KR VTN. Now if you substitute the values of things which are given in the numerical, this parameters, so VTP is given as minus 0.7, so we'll substitute it here. So let's say VTP is equal to minus 0.7. VDD is given as 3.3, so we substitute it as 3.3. Then KR and your VTN upon VTP. Okay, so you substitute them here, and we can find that, okay, substituting them here, we find that our equation will be in terms of Vout, because we don't know about Vout. So we have like two unknowns, VIL and Vout, in this equation. Okay, but if we solve this equation, okay, and you see, if we solve this equation in terms of Vout, okay, if we write this equation in terms of Vout and we solve it, then we get it, because it will become like quadratic equation. Okay, so the quadratic equation, if you see, then this quadratic equation will be a quadratic equation in terms of Vout. Okay, so you see this Vout, if you write, it will have as it is a quadratic equation, when you will solve it, you will get two values of Vout, but the other value, which of the two values we have to select one value. So the one value will be the value which is like in the range of VDD. So it should be less than VDD. So if it is if you get a value which is above VDD or below 0, so that value we have to ignore, we have to avoid it. So we'll ignore that value, and we will take the value which falls between 0 and VDD. So as this 3.14 is falling in the range of 0 and VDD, so we consider this value. Okay, and then further on, substituting the this value in the equation, we can solve it, and we can find that our VIL is 1.08. Okay, and similarly from this equation of noise margin, you can find as noise margin is nothing but VIL. Okay, and as it is not an symmetrical inverter, so VIH will not be equal to VIL but something else. So from VDD minus VIH, if you will do, you'll find the NMH as well. And to find VIH, we have to go on follow the same lines. Okay. So this was the discussion about our thing, and this problem I have taken from the book itself. So you can solve one of the, you can see one of the this numerical from the book, the example solution. So you can see that very easily and can very easily understand it. If it is difficult for you to understand, you can ask me and I'll clarify the things to you. Okay. So with this, I stop our today's discussion here itself, and thanks to all of you for listening. And here we complete over this particular unit of static characteristics. In the next unit, we'll start this dynamic characteristics. Okay, we'll start discussing the dynamic characteristics of the circuit. So okay, thank you everyone.